Hello and welcome to Empowered Learning. This particular lesson will be on what we call incrementals and differentials in taking derivatives in calculus. So we're going to start off by talking about the difference quotient and how we work up to the definition of a derivative using the limit of the difference quotient. And then from that, what we're going to do is rephrase all that you see up here in terms of what we call incrementals and differentials. And then from that point, we'll do some problems where we learn how to take a difference quotient or the derivative of a function and be able to estimate what a derivative would be or what a differential would be using differentials and incrementals. All right, so let's go ahead and get started. So we see here that we have our difference quotient here, which we can interpret as the slope of the secant line. And we know that a secant line is a line that intersects a curve exactly 2 times. If you're unfamiliar with that term or with what a difference quotient is or what the definition of a derivative is by using the difference quotient, please check out my other videos that explain the definition of a derivative. Okay? So here we have our secant line. And we see that this particular line is intersecting the function exactly 2 times. So from that, we could say that the slope of the secant line can be interpreted as the difference in between the y values for these coordinates, which we see here, divided by the difference in between the x values that we see there. And sometimes we've said that as the change in y values over the change in x values. Okay? So this is just one form. If we wrote this in terms of f of x2 minus f of x1 divided by x2 minus x1, then all we're really doing is relabeling these 2 points here. If you notice, I have x1, y1 here, x2, y2 here. That goes along with this form of the difference quotient. If I came and wrote it here, my points would look like this. So you see no big difference. The f of x1 is still what y1 is. The f of x2 is still what y2 is. If we went further along and we wanted to write this in terms of this form of the difference quotient, then my points would look like this. And again, we're saying the same thing, but just in a different way. If we kept on going and we looked at this as f of x plus h minus f of x all over h, then we see that the points would look something like this. So f of x here as the reference point, and then if we go h units over, we have this. Now the question is, where are we getting this h from? So if we look here, you see that x2 divided by x2 minus x1 here, we could look at this as just the change in x. And so we could look at it this way. And so this is what we call, this is an example of what we call an incremental. In particular, this is what we call the horizontal incremental. So the incremental is just the difference in between 2 different values, in this case, x values. Okay. Now, the change in these 2 x coordinates here, x1 and x2, the difference in between those is exactly what h is. Okay. So here, this could also be interpreted as h, because we see we have x here, and then if we go h units in addition to that from x, we have another point or another y coordinate to go with it. Okay. So here, what we call our vertical increment is actually what we've seen here before when we started studying difference quotient and limit of difference quotient as just the h here. So we could express it as x2 minus x1 or change in x or just h. Okay. Similarly, if we look here, our y2 minus y1 can be viewed as the change in y, or delta y for short, okay? And this is what's called this is the horizontal increment, sorry for that, and this is what's called the vertical increment, okay? So we have that, and so from here we could go and now rewrite our difference quotient in these following ways. So we could come here and now actually write this as the change in y over the change in x, okay? Or we could come and we could write this way. F of x1 plus delta x. And so here we see that this x here could be representative of x1, and we see h is the same thing as what delta x could be. So I could write it this way. Minus f of x1, all that divided by delta x. And so that's another form for us to be able to write our difference quotient here. Similarly, if we did our derivative, we see that we have limit of the difference quotient, and we have derivative here in prime form, derivative in Leibniz notation, and then we have all these different forms for expressing the derivative. Knowing this, we could also express the derivative using this form this way. Okay? And furthermore, we could also go and express it this way. So you can see here we're actually saying the same thing, but just in different ways. Now, again, I've said here that our delta x represents our horizontal incremental or increment, and delta y represents our vertical increment. So where does the differential part come in? Okay, let's talk about that for a second. So as we see here, we know from our theory about the difference quotient and doing the limit of the difference quotient, if we were to take this point here and continue to move it closer and closer and closer and closer and closer and closer and closer to here, we know the distance x2 minus x1, or in this case delta x, will continue to get smaller and smaller and smaller, okay? And so we know theoretically if delta x gets to 0, then whatever this particular expression here or this expression here or any of the others act like, that is what the function would be approaching for its instantaneous rate of change, okay? Now it turns out that if our difference here between x2 and x1, or put differently, if our delta x is small enough, it could be a good approximation for what the actual derivative would be. Okay? And so in that instance, we say the following. We say that here our change in y, or delta y over delta x, is a good approximation for what our actual derivative would be, with the understanding that delta x is a very small number. It's not 0, but it's very, very small. Okay? And so from here, if we wanted to get a good idea of what the differential would be, we note that delta y by delta x, or the derivative of the function y with respect to x, is equal to f prime of x. And so from that, we could say this. Okay? Now, this dy that we see here is what's called our differential. And so what I'm going to do here is show you that if we take this and we say, all right, instead of calling this dx, which is a very, very small infinitesimal difference in between the two x values, let's say we call this delta x. Something not what we call infinitesimal, but it's small enough to give you a good approximation. Then we could come and say this, that our differential, we could get a good approximation of that by taking what the derivative of the function actually is and then multiplying it times delta x. And so this is what our differential actually ends up being. Okay? Now, you're probably wondering, we did a lot of stuff just to get to something that's simple. Okay? But the point in this is for you to understand, and when we talk about the differential here, what we're really trying to do is get a good estimate of what the rate of change of something would be, taking a particular reference point. So, for instance, let's say I know that the rate of change of some particular revenue stream for a company is going to grow at a rate of whatever when we sell X1 amount of units. So that's what I have here. Okay. So if we go from selling X1 amount of units and we go up, let's say 2 or 3 more units, then the delta X would be that change in the 2 or 3. And if we wanted to estimate, well, all right, well, what's going to be the rate of change from this point if we looked at it 1 unit ahead of that? Or that would be the X2, or 2 units ahead of that. That would be the X3. So if we did that, we could get what we call a wet thumb in the wind type of estimate of what the rate of change would be. Would it be exact? No, it would not. And of course, the smaller that we make this delta X, the more exact we would probably be. But if we're taking this at a reference point of X1 and we're trying to actually measure, and let's say when rate of change at X3, we're not going to get an exact answer, but we're going to get something close. And depending on what the problem applies to, what the situation applies to, not being exact to, let's say, 10 decimal places may not really matter. You may only need to be exact to 2 decimal places. Okay. So that's the whole point and use for the differential. So what I'm going to do now is go ahead and erase all of this, and then we're going to get into some of our examples. So the first ones will be sort of skills building, showing you how we can write our difference quotient in different ways, using incrementals and differentials, and then we'll end up doing an example of where you actually see, real life example of how we can actually use differentials to estimate the rate of change given a certain situation. Okay. All right, so let's go ahead and get rid of all this. And when I get through with this, I'm just going to put the most important things back up on the board here. So first thing, we know that our delta X is going to be the difference in between X2 and X1. We know that our delta Y is going to be the difference in between Y2 and Y1. We know that delta Y divided by delta X is a good approximation for the derivative. And we know if we want to find the differential, this could be found by doing this, which is approximately equal to that. And so from everything that we've done, this is what we've got. So we're going to use this to do our examples here. All right, so for our first example, what we want to do is we're given the following information. We're given that we have a function f of x, which is 3x squared. And what we want to do is find out the following. So first thing, We want to find out the difference quotient of that written in terms of incrementals. And so we're given here that x1 will be equal to 2 and delta x will be equal to 1. So that's the first thing that we want to do. Next thing after that, what we want to do is we want to find delta x, delta y, as well as delta x divided by delta y when x1 is equal to 2 and x2 is equal to 5. Okay? So we'll start off here. So the first thing that we know is that we see that our delta 1 here, so our delta x is just 1, and we can put that right here. And we see that our x1 is 2, so we can put that there. So putting all this where it needs to be, we see that this would just be f of 2 plus 1, because the 2 comes from the x1 and the 1 comes from the delta x, minus f of 2, all that over delta x is just 1. So we have f of 3 minus f of 2. And so, of course, to find f of 3, we just go plug in 3 into the function. To find f of 2, we just go plug 2 into the function. So in doing that, f of 3 minus f of 2 would just be 3 times 3 squared minus 3 times 2 squared. And of course, 3 squared is 9, and 9 times 3 is 27. So all this is 27. 2 squared is 4, and 4 times 3 is 12. So all that is 12. So we have 27 minus 12, and we end up getting 15 there. Okay? So that is our first problem. So the second one, we want to calculate what delta x is, delta y, and delta x divided by delta y when x1 is 2 and x2 is 5. So if we start off here, we see that our delta x is going to be the difference in between x2 minus x1. So that will be 5 minus 2, which is 3. Next, our delta y, we know that's going to be the difference in between f of x2 and f of x1. So here, this would be y2 minus y1, which would be f of x2 minus f of x1. And we know that x2 is going to be 5, x1 is going to be 2. So here, this would just be f of 5 minus f of 1. And so looking there, we see that f of 5, if we come here, is just 3 times 5 squared minus, here we see this is 3 times 1 squared. Okay, so 5 squared is 25. 25 times 3 is 75. And 1 squared is 1. 1 times 3 is 3. So we end up having 72. So now we finally calculate what delta y over delta x is, and that will just be 72 divided by our 3 here. Okay? And of course, when we see this ends up being 24. Okay? So we've seen how to take our difference quotient and write it in terms of incrementals and figure out what the result is. And we've seen how to take it where we have delta x and delta y and write our difference quotient as the incremental delta y over the incremental delta x as well and do it. Okay? So next what we're going to do is work our way to the next example to where we start to use more of these incrementals and differentials together. Okay? All right, so for example 2, we want to find the differential, which we're calling dy, for this particular function. Y is 590 divided by square root of x. Okay? So as you see here, we know that the differential is equal to f prime of x times delta x. And so since we're not given what delta x is, we just have to keep it in its infinitesimal form. Okay? So first thing we need to do is know that y is going to be what our f of x is and find out the derivative of f. So here, if we do f prime, we know that this 590 divided by square root of x can be rewritten as follows. And so I'll go ahead and do that first here. We know that this can be rewritten as this over x to the 1/2, which is 590x to the negative 1/2. So if we do the derivative of it, we just have negative 1/2 times 590 times x to the 1/2 minus 1, and we'll write 1 as 2 divided by 2. Okay? So we're here. And we'll do half of 590, so that would be minus 295, and okay, so we have negative 295 times x raised to the negative 3/2 power. So that's what our actual derivative of f would be. Okay, so now from there, what we'll do is just say our differential is just going to be f prime of x times dx. So this just gives us this times dx, and of course if we want to put it in the same form that we started with, we will have the following. And so again, depending on how much dx is, will give us a very exact or not so exact form of the derivative when we plug in a particular x value. Okay? All right, so let's move on to the third example. So our third example, we want to evaluate the following: dy and delta y, or the incremental y, for this function. And we're given here that x will be equal to 2, and in this case, dx will be equal to 0.1, okay? So the point of this particular problem is to show you how the differential of a function at a particular x value and its incremental difference here is going to be almost the same, but all that depending upon how small delta x is, okay? So we're going to start off by talking about the differential. So we know that our differential is going to be f prime, dy is equal to f prime of x times dx, okay? So if we come here and take the derivative of f here, we know that the derivative of f, derivative of 30 is just 0, derivative of 12x squared is just 24x, and the derivative of a negative x cubed is a negative 3x squared. Okay, so we have all that times dx, which if we simplify it, just ends up being 24x minus 3x squared, all that dx. Okay? Now for our incremental, delta y, we see that this is going to be y2 minus y1, but here we know that we can translate this, since we have the function, to f of x2 minus f of x1. Now the question is, what is x2 and what is x1? Well, you notice here that we're given x to be 2. And then the difference in between here and the next point from a horizontal standpoint is 0.1. So when we see this, we understand this to be the this to be the interpretation here. So our x is going to be x1, which is going to be 2. And our x2 is going to be x1 plus delta x. And in this case, since we have an exact value for what dx is, we can assume here that dx is going to be equal to delta x. And so, of course, if this is 2 and this is 0.1, then that will be 2.1. So coming back up here, we know that this will be f of 2.1 minus f of 2. Okay? And so now all we need to do is figure out what this is going to be. So if we come and do that, we will have f, which is just this function here. We have 30 plus 12 times 2.1 squared minus 2.1 cubed. So that will be this part. And let me go ahead and label that to make sure that we're following everything. So this is the f of 2.1 minus f of 2, which we'll come back and just plug in 2 for everything. Okay. And so here, not to waste a whole lot of time, I'm going to go ahead and grab a calculator and do this right quick since I'm running out of room. I'll set this down right quick. And so if we do this first part, we'll see here we got 30 plus 12 times 2.1 squared minus 2.1 cubed. So this part here is going to be 73.659 minus, and then we'll do the other part. 30 plus 12 times 2 squared minus 2 cubed. That would be 70. And so the difference here would be 3.569. Okay? Now, if you look here, we actually have a numerical answer here. We don't have one here. We're actually going to now plug in the x value and the dx and show you that we're going to get a numerical answer for this. So I went ahead and just did this part, but now we're going to figure out what it actually is. So we know here that our dx is going to be 0.1, and we know that our x that's right here is going to be 2. And when we plug that information in, and I like to notate it this way, we're going to plug in dy where x is 2 and dx is 0.1. Clean that up here. We can now just plug in 2 right here and here, 0.1 there. So 24 times 2 minus 3 times 2 squared and all that times 0.1. So if we come here, this part is 48. 2 squared is 4. 4 times 3 is 12. And 48 minus 12 is going to give us 36. 36 times 0.1 gives us 3.6. So as you can see here, the actual differential gives us 3.6, where the incremental gives us 3.659. Very close approximation, although of course this is more exact. This gets us in the ballpark of where we need to be. And okay, for our last problem here, we see that we have an example of a company, and they want to sell N units of a particular product, and after they spend a certain amount of thousands of dollars in advertising. And so they've had the relationship in between thousands of dollars in advertising versus the number of units they sell, and it comes out to be this function here. And this function is good as long as X stays in between 5 and 30, which means as long as they spend in between $5,000 to $30,000 on advertising. So that may be their window as far as the minimum they have to spend in order to get any exposure, to have any sales change as a result of that. And of course, this may be their max budget for a particular time period. Okay, so we see that selling N units for a certain amount of thousands of dollars spent in advertising characterized to be this function. And the first thing that we want to do is approximate what increase in sales will result by increasing the advertising budget from $10,000 to $11,000. Okay, so when we say approximate the increase in sales, we're actually talking about increasing the actual amount of units that will be sold. So that's what that actually means. Now, notice that this does not say approximate the rate of change of increase. Okay, if we were doing that, we would actually find a derivative. We want to find the derivative at, let's say, in this case, x equals 10, plug it in and see what it is. That's not what it's asking for here. It's asking for the approximate what increase in sales. So we want to know from $10,000 to $11,000, that $1,000 difference, what would be the increase in the amount of units that they will sell or move. Okay, so here what that's actually describing is this, the change in Y, or if I put it in the context of this problem, the change in N. What is going to be the increase in sales, or the difference in between this number? Okay, so we have, let's say, a N x of 2 minus N x of 1. This is what is actually saying to approximate. Okay, if we did the change in y2 minus y1, or in this case, the change in N of x2 minus N of x1, we will be finding out the exact increase in the amount of sales, or the amount of units that will result as of changing the budget from 10,000 to 11,000. Okay, so I just want to be very upfront and say this is not what we want. We want an approximation of this. What I'm going to do right now is actually show you what this value is if we did it, and then show you what it is that the problem is actually asking us for, and show you the difference in between the two. Okay, and show you how close they are. All right, so I'm going to just label this as exact. And if we did delta N here, then of course that means we want to know what is going to be the value of N at some x2 value minus N at some x1 value. And so here we're going to say where x2 is going to be the 11,000, but we have to write it in terms of what they said here. So this will just be 11, and x1 will just be 10. So from here, this will just be n of 11 minus n of 10. And of course, this is our function, so if we plug that in, for 11, we have 60 times 11 minus 11 squared, and that would be minus, do this again with 10, 60 times 10 minus 10 squared. Okay, so we come here, 660 minus 121, and this is 600 minus 100. Of course, this part is 500. If we subtract 660 from 121, I believe we get 139, but I'm going to check it just to be sure. So that's 539. Yeah, sorry. And so if we take 539 and subtract it from 500, we get 39. So what this says here is that the exact amount of units the increase in the amount of units that will be sold based upon spending an extra $1,000 from 10,000 to 11,000 will actually be 39 units. So now what I'm going to do is actually show you what the problem is asking for and show you how we get the approximate answer and how the approximate answer is close to this one. So again, I want to reiterate, this is actually what the problem is asking for, okay? So to approximate here, we see that if we take delta y divided by delta x, and that approximately gives us what the rate of change would be. If we multiply both sides of this by delta x, then what we would end up having here is delta y is approximately equal to f prime of x times delta x. And this is exactly what we want. We want an approximation for the increase or the difference in sales. So all that I'm going to do now is just change this from y in f of x notation to n in x notation. So if I did that, this would be delta n, and this would be n prime x, and this would be our delta x here, okay? Now, one other thing I want to make sure that we understand is this x, whenever we plug it in, is going to refer to this value here. So what I'm going to do, for clarity's sake, is put x1 right there, because this is the reference amount. So we're going from here to here, okay? So when we see this, the first thing that we need to do is find out what the derivative of this is. So here, the derivative of n of x is just going to be 60 minus 2x. And in this case, I'm going to put x1 since that's there, and then times our delta x. Now, here we notice that the delta x is going to be the difference in between the x1 and the x2. So our delta x is just going to be 1, okay? So in terms of how this is written, this should actually be 10 and that should actually be 11 if we're doing everything in thousands of dollars, okay? And so the difference in between this would be 11 minus 10, which would be 1, okay? So our delta x here would just end up being a 1. So we come here, we have all this, and so now we can say that delta n is approximately equal to, and I'll go ahead and put this notation there to be clear. Let's let x1 equal 10 and delta x equal 1. So we can do that. 60 minus 2 times x1, which is 10, all that times delta x, which is 1. And we see that this is just 20, and 60 minus 20 is 40. times 1, which just ends up being 40. And so you can see here we have 39 units for the exact answer, and our estimate answer is going to be 40 units. So again, if we want an approximation, this gives us a good approximation of that.